If you can just give me a few moments here, this is Mike Pacherki. I see some people are joining a Teams meeting and not joining the WebEx. So I want to send a note to them if I can. So please hold for one moment. Okay, we're a couple of minutes past the start time here. We'll get started if we can. First of all, I want to say good afternoon, everybody. This is Mike Pacherki from America Makes NCDMM, and your host for today's America Makes Project webinar closeout. A few important notes before we kick off the event. At the end of the presentation, there will be an opportunity for brief questions and answers at that time. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen. We'll ask it during the Q&A session. We'll do our best to get all the questions answered if we can. Today's webinar is a project closeout webinar for project 5527.001, SIMBA Chain Additive with Knowledge. Led by SIMBA Chain with support from the University of Notre Dame, the project's team's objective was to lower barriers to additive manufacturing production, create verifiability, and impart production directly to supply chain data using blockchain, knowledge graphs, and machine learning. Some of the benefits are increasing efficiency and lowering delivery stress on the supply chain and empowering customers to rapidly repair systems. Without any further ado, it's my pleasure to announce our presenter, Samira Dolan from the SIMBA Chain. Samira is the principal investigator for Project 5527. Samira, I'll turn it over to you now if I can.
Yes, thank you, thank you. So we're going to introduce the project, the Additive with Knowledge overview. So I, myself, and Chuck will be presenting. For the project team, here is a list of everyone who is a part of Additive with Knowledge. We have Dr. Matthew Wells, who is the data scientist on the SIMBA side, Dr. Kirsten Storr, who is also a data science on the SIMBA side. Bob Sutton was our additive manufacturing consultant. And then Gabriel Rodriguez was a blockchain architect on the SIMBA side. Cameron Merkley was the engagement manager for SIMBA as well. And then Dr. Charles was one of the research professors, as well as Dr. Christopher Sweet as well. The project ran between September 2021 to September 2022 with a total funding of $221,900.75. Next slide, thank you. So here's an overview of the project plan. You can see a walkthrough of some of the tasks that undertook throughout the project, as well as the deliverables and the timeline that ran parallel to each of the tasks and deliverables. Next slide. Again, a walkthrough of the 9 deliverables that we went through for this project, starting at the beginning and walking through all the way down to our final report. So to give everyone some context of what additive with knowledge is, the problem statement was that there were significant barriers that existed for the production of repair parts and components produced on demand using additive manufacturing. The objective of the project was to lower barriers to production, create verification and part production directly to supply chain data using blockchain, knowledge graphs, and machine learning. Our approach was that SIMBA Chain and Notre Dame were to develop an ontology design pattern to model and reason about material transformations, given 3D files and basic metadata such as material type, size, quality, and process, and match the part to a viable additive method of part production. The tool should also be able to assess if parts previously manufactured via traditional techniques are viable if generated through additive methods. The implementation, so the lead organization was SIMBA Chain, supported by Notre Dame, and if implemented, the additive manufacturing can provide a quick and flexible solution to provide a replacement part to keep the weapon system fully mission capable. Using AWK, 3D models can be sent to the software to automatically send to the appropriate 3D printer with slicing files in queue for build, starting with GVSQ and scaling to the Army or Air Force arsenals and labs. The benefits and warfighter relevance of additive with knowledge was that it brings together multiple sources of information from public sources, data models into one unified queryable interface. The base premise, we will use knowledge engineering as the basis for the machine learning for categorizing the output device for a specific part. The GraphQL interface enables flexible querying across the supply chain to identify those parameters that do not exist today. And our AWK SCRM processing technology provides a high level of confidence that 3D printed parts will perform as good or better than the original equipment manufacturer part. Next slide, please. Thank you. So this image gives you a good high-level view of what the project looks like when all the pieces are aligned. So to walk through this use case, starting with number 1 and the bottom left corner, let's say that a driver brake pedal was broken. What happens in part 2 is that the requisition for the part is sent to DLA. And part 3, the part is confirmed, and then 3D model and TDP verified and validated into the Raptor database, which is then part 4, and put it into the SIMBA chain solution. It goes through the SIMBA process, which is going through the machine learning algorithm, and then an output from the recommendation center provides the recommendation for the additive manufacturing method. And then number 6, RIA 3D prints the part, and then that part is then sent to the original requester. Here's how the puzzle pieces fit together for additive with knowledge. Next slide. Thank you. So goal 1 being that we want to move toward a distributed self-driving additive manufacturing technique using a data-centric approach. With that being said, I'll hand it over to you, Chuck, for the next slide.
Yeah, so the approach that we're taking is what I call a data-centric approach. And a little bit, just very, very quick background. My PhD is in theoretical chemistry, material science, actually, nanomaterials. When I joined the Center for Research Computing, because I'm a model builder and building physical models and software, I became interested in how we can improve those models by basically connecting data to the models and improve understanding by connecting the data that's the output of the models to real world experiments. And this is essentially the key behind a data-centric approach. And as it this approach also. And so Andrew Nigg, who is essentially one of the fathers of running neural networks on GPUs, which sort of launched this revolution that we've had over the last 10 years, has actually started organizations that are pushing toward data-centric AI. And it's with this sort of empirical observation that you can improve performance of models, the output of models and inferencing much better with putting better data and more structured data into the models than with improving the models themselves. And so he's basically started this entire movement now to get behind and actually figure out what the best practices are for doing essentially this data-centric AI. How do we structure things in a meaningful way such that the inputs to the learning models can actually do better predictions and better performance, okay? This actually aligns with the Department of Defense data strategies that are now sort of being published. And so this is a DoD data strategy overview from 2020. But I want to call your attention to this sort of graph on the left-hand side here of the sort of goals of the data strategy, which is to be interoperable, trustworthy, linked, understandable, accessible, visible, and secure. And so what the approach that we take in the SIMBA Chain project is to use knowledge graphs and ontologies, essentially, coupled with blockchain technologies, which give us sort of that trustworthy and secure aspect as a hybrid approach, along with machine learning models, right? And so the combination of these things sort of give you that magic sauce. But it starts with the human and machine conceptualization, and so that is the place where capturing the conceptualization, a human conceptualization in a formal way that the machine can understand, that then lets you build on top of that, right? Okay, so as I said, this approach is essentially to capture that human conceptualization through an ontology, and all an ontology is it's a formal machine-readable way of capturing a human conceptualization, and then that conceptualization is combined with data, and that constructs something called a knowledge graph, okay? Who's using knowledge graphs? Well, Amazon is actually a really big fan of knowledge graphs. So on an everyday basis, if you go to search for a product in the Amazon portal, it actually, all of the product discovery and recommendation is essentially driven by a knowledge graph coupled with machine learning and automatic extraction of product descriptions, and then adding those to the knowledge graph, right? And so they have this idea of a self-driving product knowledge graph, which is where some of that terminology I said earlier of self-driving sort of comes from, right? Apple. So if you have a Apple phone, actually if you have a Android phone and you talk to Google Assistants, both of those are driven by knowledge graphs. In fact, Google coined the term knowledge graph back in 2011 or so. And so this is once again this hybrid approach of in terms of Apple of coupling essentially automatic machine learning translation to add objects to the knowledge graph. The knowledge graph then gives you, through machine learning, insights and information. Those can be done those can then support a variety of business operations, some of which are connecting to agents like Siri, some of which are connecting to other sorts of business purposes, right? Okay, so what does it take to build a self-driving knowledge graph? And so we don't really have time in this talk to go through all the nuances, but there's a very good short book, which has been published online at the kgbook.org on knowledge graphs, and they go through in very readable form the things that go into building knowledge graphs. But in general, we want to sort of start in this sort of order, and as I go through the slides, this will hopefully make a little bit of sense. But we want to start with essentially some grounding of the graph using this formal representation, this ontology thing. And we tend to use something called ontology design patterns. And all a design pattern is it's a reusable solution to a known modeling problem. And that can either be in terms of how you build a particular conceptualization, or it can be in pulling in common sense knowledge, right? Graphs that or patterns that basically capture some aspect of common sense knowledge that you want to also integrate with the graph. Then the next step is, once you have sort of this grounding, you want to basically go and start pulling in information, which may be from structured databases or CSV or other knowledge graphs. There are other large knowledge graphs like Wikidata, which I'll talk about in a little bit, which are a really useful source of information to bring in and extend out the information and instances of information that are in a knowledge graph. And then you also have the machine learning, right? And so you want to be able to take advantages of the AI in terms of pulling in text, doing named entity linking and recognition, relation extraction. And then if you're using a semantic knowledge graph, which is where what we've used in this particular project, you can use formal logics. And so you can use both inductive reasoning, which is what the machine learning sort of brings to the table. You can also do sort of these business rules sort of approach, which is the deductive side of the logics. And it's combining those two things together because they have strengths and weaknesses that essentially they complement one another. Okay. All right. So the problem is that capturing a human conceptualization is a hard thing to do, and it's a hard thing to do it well through knowledge engineering. And so, how do we approach this modular, engineering process? And as I said, we use design patterns as a, sort of a starting point for this. And the methodology that we use has been sort of summarized in this modular ontology modeling paper that was published a few years ago by one of our really close collaborators. And so it borrows from this extreme design methodology, right? That essentially in software engineering, most software is now built using this particular software engineering model, where essentially you capture user stories, you scope the project. In our case, that leads, those requirement stories then lead into what sorts of patterns do we need to essentially build from those requirements. And then we assemble those modules, those ontology design patterns in the modules. We then build tests, and then we release, and then you rinse and repeat as you go. And so you sort of end up with a minimum viable ontology, a minimum viable graph, and then you can extend it as you go as your requirements sort of grow and extend. And the way that we do that is essentially through this, as I said, the patterns in this extreme design methodology. We also use for the testing side something called Shackle, which is a shape constraint language, which is a web standard. W3C is the World Wide Web Consortium. They are the people that create standards for all sorts of things like HTML. But they also have a whole set of knowledge graph standards, which are well engineered and a really good starting point. And then we use standard software engineering tools like GitHub to basically manage the ontologies and to publish them. Okay. And so as part of that requirements gathering stage, we sort of had a set of 3 hackathons, which then informed the types of ontology design patterns that we were going to need, right? And so these outcome included, what we wanted to do is capture the sort of a domain expert's point of view and his conceptualization, if whether or not a part is manufacturable, right? Can I actually take this part? How do I manufacture it? And what are the considerations that I put into this manufacturing, right? And so we wanted to basically, do this in combination with a couple of different experts, because we tend to get what's called frame lock. And so if we sort of dive in and focus on a particular aspect of it, we may miss other aspects. So we like to have lots of different sort of points of view. The nice thing is that we had a domain expert from that was our TPOC from the Army that participated in the sort of hackathon, went through, captured a variety of notes. Okay. The first hackathons were aimed at competency questions. So competency questions are things that we want to ask of the data, and they sort of ground the conversation of what sorts of patterns we may need to answer those competency questions, right? And so some of these competency questions are like, from a material side, what sorts of materials can this part be manufactured in, right? Will the orientation of the part be able to sit on that particular proposed manufacturing device, right? Heat transfer, orientation of the particular part in terms of supports, all of those sorts of things. Post-processing, so what sorts of things do I need to do to this idea of minimization of post-processing? Infill for polymer parts, right? Second hackathon was looking at tolerances, right? And so these are sort of looking at, this mapping between a 2D geometry and essentially a 3D geometry, and how a human being might go about adapting that. Those inform the sort of machine learning side of the models, and sort of what sort of information can we use neural networks to essentially extract that information from the 3D model, and that will guide those sort of activities. And then the third hackathon was on the actual printer side. So what sorts of things do we need to connect from the sort of point of view of the part that we're wanting to print to the thing that then can produce that part, that technology, right? And how does the process, quote unquote, material transformation process, which I'll get to here in a little bit, how do those impact whether or not that particular part can be manufactured with the design specifications that were originally intended in the part essentially design specification? And how do I enumerate even that design specification in a way that the machine understands, which is the data-centric AI part, right? Okay, and so as part of this, we also like to survey existing conceptualizations. And as it turns out, there were a couple of existing quote unquote ontologies that were sort of developed to take into account additive manufacturing, right? And so some of these were developed from actually a biomedical ontology point of sort of approach, which is this product lifecycle ontology, Barry Smith. The other ones were developed more from a pattern based. And so we took a look at these things, and this is an example from one of the papers that uses sort of a pattern-based approach, not a complete pattern-based approach, but it uses something called Dolce, which is what's called an upper ontology, and basically lays out what, essentially the existing concepts in terms of process, material, objects, physical artifacts, and then a lightweight typology to go to the process type. And as it turns out, this is a pretty useful way of modeling the data, especially from searchability. So if you want to do GraphQL or Sparkle queries of the underlying data, if you have to walk through a deep sort of class hierarchy, it can become inefficient. And so these are sort of the more software technical engineering sides of that you want to sort of consider. And so this was actually a pretty good approach. When modeling with domain experts, we tend to capture things in terms of a concept graph. And so this is a sort of one of the first sort of what I call straw man. When I'm modeling with a domain expert, I create a loose straw man design pattern, which basically has the basic concepts of, what an object is, a physical object, which is just a thing that's composed of matter, a physical artifact, which has some purpose or intent, maybe designed by some plan, a design artifact, which has then some formal design and a design specification that's behind it, right? And then those things become part of this idea of a functional system, right? That these maybe component parts of some sort of system that you want to keep track of in your knowledge graph, and in each of those components may be a manufacturable component, right? And so having this information as sort of a starting point for doing the modeling then lets you evolve that model in sort of a controlled iterative manner. And then the next step is to formalize this, right? And so there's actually a web ontology language called OWL, which is a W3C, once again, web standard for exchanging conceptual information on the web as data. And so there's a really nice tool called Graphu, which we sort of took advantage of with the sort of modeling of this as starting points in terms of the design patterns and modules. Then, so on the right-hand side, you can sort of see the conceptual patterns. Left-hand side, you can see what the output of that is in terms of the actual ontology model, right? Okay, so one of the things that we wanted to do then is think about how do we incorporate sort of standards for describing material science and material data. And so Nanomine is a project that was part of the Material Genome Project that I actually have some experience with several years ago, modeling with some domain actually I was one of the domain experts, ironically enough, from the National Institute of Standards, and so and also NSF, so it was sort of jointly funded. And so they're in this case they're reusing essentially conceptual components that were developed for biological sciences and the life sciences, which have a much richer history of essentially trying to capture domain knowledge in medicine and life sciences and integrate those into knowledge graphs, particularly things like the gene ontology, which has revolutionized essentially protein science now. And so we wanted to be able to leverage those existing chemical description language and those polymer description languages and the material science sort of description languages. And so we're definitely integrating things called the semantic science integrated ontology, which is a very lightweight approach to essentially these life sciences, which give you this idea of these sort of core things as processes, qualities, those sorts of things, and component parts, so a lightweight meteorology. And so that's what we're bringing in. Okay. And so we borrow from the semantic science integrated ontology, this idea of a process and how that relates to an entity. Now, process doesn't mean process is very generic, right? But it gives us that existing structure, conceptual structure to start to bring in that processes are, they have time intervals, they involve some objects, and they involve some entity, which is what's called a realizable entity, okay, which may have some attributes, role, etc. Previously, I published a paper on material transformation, and this was essentially to track lifecycle analysis in architecture and in the building engineering space. And so the idea was that if we're building, buildings and want to understand the energy and carbon and all those impacts, we need essentially to do cradle to the grave sort of analysis based off of the designs that are being generated by an architect. We need to do that front to be impactful. And so this pattern was essentially the design so that in the knowledge graph, the transportation costs of something from one place to another is a trajectory that was well modeled. When things change identity and you have this sort of step where you have a material transformation, that becomes a little bit harder, and we want to know the energy and the costs and impacts of that. And that's where this pattern was originally designed. The application was designed for, but because it's a pattern, it can be reapplied to different applications. And so that's essentially what we did with the additive manufacturing, is take that existing design pattern and put it into the additive manufacturing context to answer those questions as data is added to a knowledge graph, right? And so this is an example of how we did that alignment in terms of saying that there's an additive manufacturing process, which is part of that's an SIO procedure. So that the additive manufacturing is a procedure, it's a set of steps, and then there's essentially this transformation, which is the implementation. It's the realization of that sort of set of steps to produce a real concrete thing at the other end. And so we can then take that as sort of a conceptual building block to put into the knowledge graph and build out further. Once again, web standards for interoperability. And so that pattern, that previous pattern, as I said, that sort of links to these these external ontologies in orange and red. We don't want to reinvent the wheel. And we want this data interoperability. Remember from that original product statement or problem statement, we wanted to be able to take information and data that was spread all over the country in different commands, different locations, and connect that together. And so we want to use standards and standardized vocabularies to be able to do that connection. And one way we do that is the OWL time ontology, which is a standardized way of exchanging temporal intervals, temporal information. In particular, I've done work with the OGC and W3C to add in this idea of a temporal aggregate of how do you create essentially collections of temporal information and be able to do sort of temporal reasoning over that. So that's part of the process. The other thing is GeoSparkle. And so GeoSparkle is a way of querying spatial data. So these things occur in time, they occur in space. Questions you want to ask of the knowledge graph in terms of manufacturability involve time and space. And so we wanted to create this interoperability layer using those standards. And then we also need to connect back to the blockchain, right? And so from an interoperability layer, that a particular material that's a manufacturing material that may go into that's a printing material that may go into your additive manufacturing process, right? That material transformation as an input. Those are products in and of themselves, right? And so they may have manufacturer information and tolerances and all sort of information. And so we want to create this interoperability layer using GS1 sort of standards. And GS1, they came up with the barcodes. They're the inventor and standardization of that. They now have moved to blockchain standardization in terms of product and those sorts of vocabularies on the web. And so we have sort of loose coupling to those sort of vocabularies also, which brings in sort of this secure smart contract ability in the future and these other sorts of things. Quantities, units, dimensions, and time, right? And so one of the things that we're talking about actually in those use cases is how do we capture, tolerances that may be associated with the design specification. And so the way that we do that is by using an ontology. It was originally developed by NASA, actually in response to crashing a very, very expensive probe into Mars. And how do we then be able to leverage that vocabulary to basically quantify in a machine understandable way what a value is and what a quantity kind, what does that respond to? And it also lets you do unit conversions, right? It defines whether a unit is commensurate with one another. So it has this idea of dimensionality. And so it's a very useful way of taking a design specification and creating a formalization of that design specification that then is machine actionable. Okay. Lastly, I won't talk too much about this, but it also fits into another standard called the semantic sensor network standard, which is sort of this Internet of Things. It builds on that. So if you have smart applications at the other end, you can integrate sensors and observations and all these sorts of things. It also would support quality control, all these sorts of other sort of applications. Those are left as stubs. And so we know that they could be important, but they're not part of the scope of the requirements for the current project, right? But we know that because they're important, we want to leave essentially a hook where you could then extend that later on, right? And that's part of the ontology engineering process. We are big supporters of FAIR. So this is findable, accessible, interoperable, and reusable. In fact, there's an entire set of recommendations developed by the Research Data Alliance on how do you create a FAIR ontology or a FAIR vocabulary as a starting point that other people then can use to create FAIR data objects. And so we use those recommendations as a way of structuring the ontology. And those include, we created W3ID namespaces. So these are persistent identifiers. That means that if somebody is using our ontology and this web URL address changes, it doesn't really matter because it's based on this mapping to a persistent namespace. And so from that perspective, their application can keep functioning even though the ontology may have moved from, say, GitHub to a server somewhere in the world, right? And this allows you to then, sort of smooth over perturbations to essentially the engineering flow. We provide multiple serialization. So there's something called Turtle, which is a way of creating a machine readable document. JSON LD, we provide those through content negotiation. Means the machine can ask for whatever representation is appropriate for the application. We provide human readable documentation and versioning. And so the documentation, the HTML web pages that document the ontology are essentially built directly from the ontology. And so this way you have this integrated workflow of the documentation is produced directly from the underlying information. And we also, as I alluded to, use web standards for that serialization, right? And so this is an example of the documentation that gets, that's FAIR documentation that gets produced through a tool called PyLoad. There's a couple of different tools for this. We chose for this particular application something called PyLoad. And so you can sort of see the human readable information on the right-hand side. That's generated from the machine readable information on the left-hand side, right? Using standardized vocabularies. Once again, FAIR. We want to be able to link to things, which is what the Department of Defense was saying. It's built for modules. And so each of these sort of ontology patterns get wired together into a module that then we can develop out independently. And then those get built into a development sort of deployment that we can then check through, do consistency checks, those sorts of things. And then we actually do releases, right? And well, we do testing, and we use this test anything protocol, which is a way of using essentially shell scripts to then do the underlying testing based off of the shackle shapes. And so as applications come along and you're building the knowledge graph, this is at the knowledge graph construction stage, you can test consistency. You can also we also do some syntactic validation checks in the repository, make sure that we don't have typos in the documents and stuff like that, so that way they're machine parsable. Okay, we automate these using GitHub. And so GitHub, if you don't know, has this wonderful set of tools called GitHub Actions, which essentially let you, when you do a push to GitHub, let you trigger a certain set of tests. Those tests then can tell you that, uh-oh, I have a problem, as is indicated here, that there was an incident, there was an error in one of the files in terms of a typo or something like that. It can go through, give us humans understanding that there may be a typo, and we can fix it. Okay. Knowledge graph construction. Okay. And so now we're getting in sort of this hybrid space of how do we take something that is the machine logic representation and then use machine learning and neural networks and those sorts of things. And so there's this wonderful graph data science library, which is sort of the Swiss Army knife that my students absolutely love. That lets us do that connection. And we use something called Jupyter Notebooks as a way of doing that exploratory data analysis and developing out the models. Those can then be transferred into any software pipeline and automated and pushed to production once you have sort of the data science and the connection, sort of ironed out. The way that we do that right now is we've taken those sort of domain expert, knowledge and put those into spreadsheets or CSV files. And those CSV files then, along with the graphs, let us communicate with someone who's not an ontology expert, right? They can readily look at a CSV file and say, no, this is not exactly the correct terminology for this particular, overhang tolerance, for instance, or this is not the correct specification for that particular machine. And so we have essentially two different different design specifications. One is for the additive manufacturing system. So this is the type of printer, what type of system it is, what its design specifications are, and then give us the ability through machine learning to match against the design specification, which is the design specification of a particular component part, right? And so that's what you can sort of see on the right-hand side is the part thing that extracts information from a CSV, and on the left-hand side, you see the specification for the additive manufacturing machine. And so we basically have two different CSV files that then get loaded, and this is an example of the code that essentially does that loading using something called Pandas, and then builds a knowledge graph based off of that. Now, all of this, because this is at the first step is prototyping and sort of hand-driven, this can all be automated. And so I can use something called Morph, which is essentially a way of doing that mapping in a machine-centric sort of way. So once everything is sort of standardized and we know we like it, and it's answering the domain experts' questions at the other end, we can automate it. And the same thing also with using essentially machine learning models for this sort of text extraction. So just as I alluded to with Microsoft, with Amazon using product descriptions to build their knowledge graph, we can also do the same sort of thing in the process. We leverage existing knowledge graphs like Wikidata, and so we can pull in information that already may be existing in Wikidata, which is run by the Wikimedia Foundation. They're the same people that do Wikipedia. In fact, it's driven by Wikipedia, and so we can pull in additional information on manufacturing machines, process, and link to those in the ontology. And it uses a web standard interface, way of basically building these APIs, something called Sparkle. And so I can automate that through software and queries to the knowledge graph to then automate building of the knowledge graph. And so, for instance, we have these crosswalks in our ontology to material types that are already present in Wikipedia and Wikidata that may already have information that is qualities that may be associated with that particular material, like a tensile strength or pitting resistance. And the nice thing is that because they use machine learning internally in that large knowledge graph, they look for consistency checking. And so the idea is that they can basically go through and do this sort of where you see on the screen this exclamation mark, right? That there may be an issue with in terms of there's a qualifier. So the tensile modulus, right, is at a particular temperature that modulus applies to, right? That modulus of elasticity. And so without that qualifier, there's an issue, and it can give you essentially this sort of feedback to that. The nice thing is because it's there, we can already sort of take advantage of it. We hand check it, at this point to make sure that it's sensical. But it lets us, we don't have to start from scratch, essentially. And this is a well-known approach in the life sciences community. So, this Wikidata material ecosystem, I think, sort of as a pet project, needs to build off of sort of these lessons that the life sciences have come up with. In fact, they can do this automated structure sort of searching, which, as the chemist in me absolutely loves. Would have loved to have had that 15 years ago. Okay. We also then need to be able to connect to the software that SIMBA Chain is bringing to the table. And the way that we do that is through using essentially these web-based frameworks for querying knowledge graphs. And one of them is something called Communicea, which is developed in combination with Tim Berners-Lee, father of the World Wide Web. He has a new project called Solid, which is aiming to decentralize the web and create that sort of distributed knowledge graph-based infrastructure. This lets us do something called GraphQL-LD, which gives us a context for the underlying objects that are in this data file. And that links to then the knowledge graph. And so you now can either query this as just a thing for doing web form development, or you can query this as a thing that has deeper understanding and use for machine learning. Okay. Okay, so we're coming very close to the end of our talk, but I just want to give you a flavor of how this sort of fits into the machine learning part, right? So how can we sort of use this to build hybrid AI? And this is work that, we're sort of haven't done, but we were laying the groundwork for, and this is what's coming up to give you a flavor. And so one of these sort of interesting pages on that DataCentric AI page that I put at the very beginning of the talk, right, is this idea of a visual genome. And this is Professor Fifi Lee, who is on the board of Twitter, on the board of many, many different things at Stanford, sort of came up with 6 or 7 years ago. Her student is actually head of AI for Tesla and their self-driving vehicles. They most certainly use these sort of scene graph idea in order to connect concepts to the sort of image segments to give more signal to the neural networks as to the context of what something is, right? And so we want to sort of leverage that, right, in some way, right? And so there's this really interesting paper using common sense knowledge graphs. So Wikidata actually has bits of common sense in it for essentially doing this exact same sort of annotation, right? But it's actually based on properties that aren't just arbitrary sort of properties. They are actually formalized in terms of those semantics in the knowledge graph, right? And so you do the same sort of idea and do the segmentation. Now, why might we want to do that? Well, might we want to do some of this sort of common sense grounding? And so, in the last 3 or 4 months, this is, well after this project started, we are now getting these, sort of applications of AI generators, right? Like DALL-E and image gen and stuff like that. But they are more than willing to go and create based off of a sentence, a scene, but that scene may or not be sensical, right? And so on the right-hand side there, you can see a cup, right? Where essentially the input to it was a coffee cup with many holes. Now, the machine has no idea of containment, what the concept of containment is, or the physics that may be associated with containment. And so it is perfectly happy with generating an image of a coffee cup with coffee in it with many holes. But we know from human common sense that if we had that cup, there would be a puddle of coffee surrounding the object, right? And so we have this deeper understanding. The machines don't quite have that understanding. They also have issues with counting, and that's what that center one was sort of aimed at getting you to, right? And so the hope is that if you can combine knowledge graphs and knowledge graphs that have been constructed using patterns that sort of have this common sense understanding incorporated into them and give you this sort of scaffold, that you can improve the performance of these models and give them a little bit better understanding. And so in that paper that I alluded to 2 slides ago, they did a little bit of experiments in terms of the scene generation, and it's unfortunately pretty hard to see from the images in the paper. But the idea is that you can look at a scene generated without common sense knowledge, that the scene generation actually in C is that it's a rider with a helmet and etc. And so without common sense knowledge, the helmet may not be present, it may not be present in the right place. But with common sense knowledge, it has the scene graph that you see on the left, which then contextualizes that, a helmet is an object for safety that a man is wearing, and it's so you can see how you can give more context to the machine to enhance the actual understanding and neural network generation. That combined with essentially a differentiable way of looking at the geometry, right? And so in those scene graphs, they used convolutional neural networks for the image recognition, and then used essentially language models, graph models to then combine together the description and the knowledge graph parts. For three-dimensional geometries, we need a little bit different way to do that. And so there are these methods for using essentially NURBS as sort of the standing point. So NURBS are well known to, to CAD geometries, doing meshing and stuff like that. But differentiable NURBS are essentially a way of taking that and creating it a mathematical representation so we can do back propagation. If we can do back propagation, then we can do segmentation, we can do all these sorts of things, and then annotation and learn over them. We can train them along with all the other information in the neural network. And so you can sort of get a flavor of how these things might fit together in a way that then creates a end-to-end neural network that can take some domain expert in the middle, human in the loop sort of annotations, combine those together with machine learning to build recommendations at the other end. And this is sort of the architecture that we're exploring right now. And with that, I will leave the sort of last slide and let Samara comment on that, and I guess we can take questions.
So thank you so much, Chuck, in giving us the overview. And just to follow up with what you were saying around the future work and where that leads America Makes and Additive Knowledge, here's again bringing out that high level view of how all the parts fit together and what the vision and goal is of the recommendation center being a part of this entire cycle from imagining fracture being requested to the final additive manufacturing process. With that being said, if we have any Q&A, I don't see anything in the chat yet, but if you do have any questions, we are watching the chat box for any Q&A at this time.
Thank you, Charles and Samir. Thank you very much for the presentation. Very informative today. Yeah, I don't see any questions coming through yet at this time either. We can give a couple moments maybe to look for them if possible. The only question I was going to ask was really dealing with this last slide, I guess, was the future work. I know this project coming to an end here in September, and just looking forward to what you would like to do if you had more opportunity. Would this basically describe what you're looking at trying to do here in the future?
Yeah, so I mean, sort of this first phase that we just did was laying the sort of conceptual groundwork. So I hope that everyone sort of got this flavor of how we're trying to essentially build a foundation that you could then put into a distributed framework like what SIMBA Chain has, that then would essentially allow use cases which are outlined in terms of what is on the slide. And so we already can take three-dimensional files. We can we've defined metadata that is part of that process that needs to be added. Those can be used to generate added to the knowledge graph using this sort of semantic ontology scaffold. But those are also distributed, right? And so the idea is that the interoperability layer, which I didn't talk about a lot, right, is a key part of this, right? So if you'll notice in this diagram, right, that these are all distributed endpoints, right? This isn't some centralized thing, right? Some giant brain, right? So the idea is we want to create interoperability layers for these agents to be able to talk to one another and be able to exchange in a common vocabulary the information that they need in order to sort of realize this vision, right? And so yes, that 100% is that sort of that next phrase that we would like to do is essentially start to build out these little modules that then are distributed in using SIMBA Chain's underlying core sort of technologies, but then also integrate with sort of this machine learning bits that we've been doing to add value. I don't know if Samir wants to, from the PI's
No, I
perspective.
think you definitely did the question justice there. Thank you, Chuck.
Is there any other questions coming in? I don't see any other ones right now. Just at a high level, because I know a lot of people don't understand blockchain. Can you explain blockchain at a high level for people here on the call?
Yeah, so blockchain, think of it as a distributed, verifiable, immutable ledger. And so, what a blockchain ultimately, I mean, originally, so it has this sort of connotation with, NFTs and all these sort of things that my generation, in fact, I'm not even certain I understand NFTs completely. But the idea is that I want to be able to create something that the first word distributable, right? So the ledger itself is something that anybody can get and look at. Immutable, that means that if I put something into it, right, it's basically sort of hermetically sealed. And so that way it's verifiable. I know that somebody didn't come in after that and essentially do some mutation or some permutation to it, right? And I can store whatever I want to on it, but the issue is that the more things that I store on it, the more expensive that it is. And so I want to be very judicious in the immutable bits so the things that need to be immutable, like say a contract, right? A specification of a contract, those sorts of things go on to the blockchain. But because we're using these sort of decentralized knowledge graph things, right? And there's an entire set of standards which people, have just been approved by the World Wide Web Consortium 2 months ago. called decentralized identifiers. And SIMBA, it was an early leader in terms of adopting these decentralized identifiers. And so I can put a decentralized identifier, that identifier on the chain, but that can link to things that are outside the chain in terms of a knowledge graph. They can also be signatures, right? And so I can go through and do a cryptographic signature, put that on the chain. I know that that signature is immutable the way that it was calculated. And then I can go and verify something that's off chain using that, right? And so this gives me essentially that flexibility to go and do those sorts of things. Everybody can look at it and agree that this thing hasn't sort of changed in the process. And I can set up the idea of smart contracts, right? So these are things that are sort of immutable, auto-executing sort of agreements, right? And so as supply chains are becoming more automated and more complex, you know, those sorts of technologies sort of integrate. And these are all using these, you know, these decentralized identifiers and all these W3C standards use those same data standards, excuse me, that I was talking about in terms of JSON LD and ontologies and those sorts of things, because they're building on this rich data history that the World Wide Web Consortium has since the late 1990s. And so they all fit and mesh together quite well. Did that help?
Sure, it helped for me. Thank you very much. I do appreciate it. I do not see any other questions coming in at all at this time. I guess I would make the comment that we are, I guess it was recorded, so the recording will be off, you know, for people who need to see it afterwards. They can watch this afterwards. But I do want to thank everyone for participating. Unless there's any late questions coming in here at all from the attendees. If not, I want to thank you know, Samira and Charles for your time today presenting this. It was very good. I guess if they want to have any questions to follow up at all, I guess I think everyone has your email addresses too.
And if you haven't noticed, I love to talk. So please, if you have any question, just reach out.
So I see a question come through here, and take a look here. Jason, can you help me find the questions on here? I saw something pop up.
Yeah, let's see.
I think I
No
lost them.
questions. No questions.
No question. Okay, I saw something up.
There were some comments.
Okay.
No actual questions. I'll
Okay.
pass I'll pass the comments on to the team so you guys can read them after. It is quite interesting.
Excellent.
Okay, well, I do want to thank everyone for attending today, and again, we'll have this available on the digital storefront for everybody afterwards. And if there's any other questions for me, please get hold of me. If not, I do appreciate your time today, and have a nice rest of the afternoon.
Thank you.
Thanks.